Excellent. We're going to have next Professor Aaron Baggish, my dear friend, who's currently at the University of Lausanne in Switzerland, and he's going to be talking to us about monitoring devices from wearables to ILRs.
All right. Good afternoon, ladies and gentlemen. Very, very delighted to be here with you. I want to thank the folks from CRI, EAPC, and the ACC for putting this together. Big shout out to Jonathan and Michael for all the work. As someone that lived and worked in Boston for 20 years and now lives in Lausanne, Switzerland, it's delightful to see both European, American, and even some people from a lot further away getting together to collaborate on education. So thank you all for being here. This is certainly a momentous event. My task this afternoon in 8 or 9 minutes or less is to talk about wearable devices, and this has become an incredibly complicated part of how we practice sports cardiology, but I'm going to give you a way out. For those of you that don't want to engage in this, I'm going to explain to you why you can not do so, and for those that do, hopefully give you some key points to do this well. All right, so let's be clear. In 2024, we have wearable devices that can be placed on any part of the body to answer any question you want. Whether it's a performance question, a health question, a marital status question, I don't care what it is, there's a wearable device that can be sold to you. These wearable devices now are not typically freestanding. They're linked to some sort of commercial software that allows analysis, download, and even sharing with your doctors. And what you can see here by this projection here on the bottom of the screen is that the wearable market, and these are data from the United States, is just simply going to increase over time. So what this means is that our patients will be buying these things, they will be using them, and they will be bringing them to us to ask for information and help. So where we started, this is 40 years ago, Pollard invented the first heart rate monitor. I remember putting my first one on in 1989. It had one functionality to it, and that is it gave you your heart rate at rest and sometimes with exercise. Now these have become universal health and fitness tools, and there's no escaping them. Where did it all start? Most of you are probably familiar with the story. The first commercial wearable was disseminated in 1965 in preparation for the 1964 Tokyo Games. It was called the Mampo Kai, derived from the term mile, which comes from the Latin word millipasum, which stands for 1,000 paces. And one of the simplest things that come from wearables, and we do this every day, is the idea of step count. And step count can be used as an exceptionally useful way to give people an idea whether they're getting enough habitual physical activity. You can see here data published in JAMA Open, which show that at approximately 7,000 steps per day, we start to appreciate a mortality benefit. That mortality benefit is statistically significant up to about 15,000 steps, and then it looks like maybe if you walk too much, you get sicker. Please don't believe that. That's a statistical error. But suffice to say that steps are a good place to start with our patients. So one of the decisions that you all have to make in your clinic is you have to ask yourself the question, am I going to integrate wearable data into my workflow with my patients? And I would say, as Yoda says here, do or do not, there is no try. The reason for this is that if you try and you're not committed to it, you're likely to waste time and not give the patient the information that they want. If you commit yourself to it, you understand the physiology, you understand the technology, there's a lot that can be gained from this, but it's not for everyone. So what are some things that go into answering this decision for you personally? Well, it starts with understanding the technical and the physiologic knowledge that's required to both understand the device as well as the metrics they measure. There's having the adequate time. Do you have time built into your practice to actually sit and review Garmin tracings with your patients? Not everyone does. At present, there are no commercially available fitness devices that are advocated or approved by agencies at medical grade during exercise, so this is another important thing to consider. And then finally, the use of commercially wearable fitness trackers for health outcomes are not yet guideline supported. That may change, but if you're looking for reasons to use them and not to use them, here they are. If you're interested, this is one source of information. This is a state-of-the-art paper that my Boston-based group put together just last year, looking at wearables in cardiovascular medicine. There's a lot in there, and I'm going to show you a couple of figures from this. So what do these devices advertise they provide? Well, essentially everything you could imagine: exercise load, recovery, health status, performance potential, sleep quality, caloric expenditure, pulse oximetry, arrhythmia, detection of acute illness onset. And the devices do provide readouts of these things, but what I want to remind you of is that the devices make these estimations about these parameters from a very, very, very small number of things they actually measure. So what do these devices measure? They measure time, which is simply the stopwatch or chronography. They measure motion using accelerometers. They measure heart rate and respiratory rate, either using PPG technology, which we'll get back to, or touch electrodes. Pulse ox, same. And then increasingly, we see devices that can measure a single lead ECG, which is done by some two-point contact, and those varies from device to device, still not useful during exercise. But importantly, these all have heavy reliance on algorithms. So when my patient comes in and says, my device tells me I'm abnormal or my device tells me I'm normal, we have to remember the reference populations that the device users are using for these, and far and away, they are not the people we see in sports cardiology clinics. So PPG, if you're going to be working with athletes that use a wrist-based watch that measures heart rate, this is the technology that underlies PPG. Put very simply, and you can see the back of the new Garmin Epics there, there are light electrodes which shine light into the skin. Those are reflected by blood vessels in the dermal capillaries, come back to the watch, and the watch is able to calculate pulsation or heart rate. Also respiratory rate done the same way. This, when plotted over time, gives us a look at exercise during heart rate, and so these are what our patients are coming to us with. Now, pleth is not perfect, PPG is not perfect, and there are a number of things which get in the way of pleth measurement. Here's a list that we put forward in this paper, and the three most common ones I just want to run you through. Any individual with darker skin color is going to have less accurate results with pleth. That's just the way it works. The transmission of light is less optimal when people have a lot of melanin in their skin. The second is tattoos. So when patients have tattoos on their wrists or wherever the device is going to be used, this interferes with PPG. And the third and the most important is normal human anatomy. So anyone with an ulnar styloid that looks like that will almost certainly get no watch contact on their wrist. And so when people come in, look at Andre's got a beautiful one there. When people come in and they have problems with watch contact, have them flip the watch onto the soft fleshy part of the skin and you'll get better results. So, a quick word about HRV. Most of you are familiar with the concept of heart rate variability. This is not new. This was developed decades ago to look at outcomes in the intensive care unit. All heart rate variability is simply measuring the R to R complex time variability over different periods or different frequencies of time. And in the sports cardiology space, our athletes love HRV because it is one potential way to look at rest recovery and the overall balance of sympathetic and parasympathetic tone. But when an athlete comes in with disturbed HRV measurements, they've gone too low or they've gone too high, I want you to remember that this raises a differential diagnosis, and overtraining or overreaching is the diagnosis of exclusion. There's a lot of other things, and you can see them here: sleep quality, diet, psychosocial stress. All of these things can contribute to HRV variability, and we really want to understand how to talk to our patients about this. So here's a typical heart rate tracing, which in isolation really doesn't mean anything. This is heart rate plotted by a nondescript time axis on the x-axis here. And what you can see is there's some ups and some downs without overlay. And I'll get back to what overlay means in a minute. So when your patient emails you one of these at 6 a.m. on a Monday morning and asks what to do with it, you got to know how to start asking the right question. So the first question is, who is the patient athlete and what were they doing? So this is a 48-year-old female who was using monitoring during a 3x1K track workout. And so question is the heart rate within expected physiologic limits? We need to look at the y-axis, and indeed, ranging from 120 or so, it's starting up to maybe 170. That's probably physiologic. Are there clear spikes? Well, indeed, there are clear spikes in variability, but the question we want to know is what's happening during those spikes? And we start by asking our patients, why are you showing me these data? Did you feel the spikes? And in this patient's answer, nope, felt great, crushed it, just wanted to see how fit I am. So, when we look at these, one of the things we really want to try to understand is there consistency between heart rate, which is a measure of internal work, and some measure of external work, whether it be speed running, wattage on the bike. And so in order to do this, this is something that most commercial vendors provide you with, we can rely on overlays. And I'll show you a little bit how overlay works. So this is the same workout now with a messy but instructive real-world overlay, and this is overlaying the pace of the runner during the heart rate monitoring transmission. And what you can see here is that the pace, which is reflected by these squiggly blue lines, indicates when the athlete is going faster, when the athlete is going slower, and importantly also when the athlete stops completely. And so if you look here, there's clear heart rate work concordance. Times the athlete stops to rest, stretch, prepare, heart rate drops. When the athlete enters the intervals, you can see they go up nicely. And so these positive spikes are pace concordant, and this is simply the workout that was recorded. Same with the stopping. The negative spikes are concordant. These are deliberate pauses for stretch and recovery. How about when it doesn't necessarily work that easily? This is a 25-year-old man monitoring his heart rate during a 5x1K run workout. And I said, tell me about this run. Why are you showing me this? Well, all was fine until it wasn't. Fourth interval, I felt my heart take off and I got super dizzy. It went as quickly as it came, and then I just finished the workout. So let's put a pace overlay on it and see what happens. This is a different type of pace overlay. This is a lap average speed, so it's looking at the variability in speed on interval, off interval. And you can see during the fourth interval, as he started, all of a sudden his average lap pace went way down, while his heart rate went way up. So what's happening here? He's developed a paroxysmal arrhythmia that's compromised his cardiac output. He feels that, he stops, and so there's a clear heart rate work discordance. This is an indication, very high pretest probability of underlying pathology. Internal loop recorder confirmed narrow complex tach at 230. He went on for an EP study, ablation of a nodal tachycardia, and did well after that. So a quick word about the Frontier X device. They are a sponsor of this. This is a device that I know several of us in the audience are interested in and are starting to use more frequently. What's nice about the Frontier X is it provides single lead continuous ECG recording with actually very high fidelity during exercise, and the ability for an athlete to record it as well as push trigger sensors so that we and doctors can go back and look at it. So here's a 24-year-old female with exertional palpitations that came to see me in clinic. She had a family history of sudden death. And she says, I felt like this morning on an easy jog, I was wearing that belt thing that you gave me. I pressed the button and then walked home. Here is what I downloaded. Boop. So this is her during her run. You can see the histogram of her heart rate response during the time of her exercise. You can see a patient trigger there with the black dot, and then you can see the non-sustained polymorphic VT as an indicative. And in her case, normal imaging and normal exercise treadmill test, but she went on to have a PKP2 gene mutation positive for arrhythmogenic substrate. Discussions about ongoing return to exercise as well as ICD were had. She opted for an ICD and is back to running. So finally, a little bit about implantable loop recorders. Depending on where you practice, whether it's the US or Europe, you will have different devices that are available for you. They are with subtle abnormalities based on time of battery life, how things are downloaded, what the patient experiences. They're all pretty similar, but the general utility of these in sports cardiology practice is to look for relatively uncommon or very concerning things that need long periods of time to capture. This is an old study, but it remains my favorite ILR data set looking at the yield of what we would term conventional ambulatory rhythm monitoring, so extended duration Holters, versus placing in a loop. And what you can see here is that when we rely on a conventional diagnostic strategy, we only find about 20% of the pathology. When we go ahead and put in a loop, we flip those numbers around and we're closer to 75, 80% in terms of pathology detection. Other thing embedded in this study was the idea of ILRs actually being cost effective, which they are. So low threshold to put this in, again, in people that have relatively infrequent but concerning symptoms. You'll oftentimes find diagnoses that can both be reassuring as well as confirmatory. So just to conclude, I think we are just seeing the tip of the wearable iceberg. These will continue to be more and more a part of our practice. Again, I think it's very reasonable right now for you to ask the questions that I posed and decide that you don't want to tackle wearables. But if you do, coming into the room with a basic understanding of the technology in the device, as well as the physiology underlying what the device tells us, is absolutely important. Thanks very much.
Thank you, Aaron. Do we have any questions from the audience? There's a question. So while you get the microphone, Aaron, if I may ask you a question. So obviously, I am going to bring up the younger population, obviously bias, complete transparency. However, when we think about, it's not only elite athletes that are out there, probably most people exercising are our children, right, while they are in school. And it may not be 16, 17, but it may be 12, 10, 12. Where do you see these monitors potentially helping us?
Well, with children, we have a public health crisis, right? Whether you live in Europe or the US, we recommend our kids get 60 minutes of physical activity a day, and I can promise you that the vast minority of kids in either continent get that. So we have to start simple. I would love to see step counting be a routine part of school and build in times where steps were mandatory. Whether that will ever happen, I don't know, but doing something is better than doing nothing.
And I think certainly having those parameters that are actually validated in a younger population, because I think it's something that we are missing. Please.
Thank you very much. That was fantastic. My question is about how are we going to deal with the onslaught of the data of millions of wearables, especially if they come up with some data like the ones you showed us, some really serious. I mean, these are medical devices. Very large tech companies like Apple Watches have thrown them into the public arena, and they have not taken any accountability on filtering the data. Do you think governments should force them to spend some more money on responding to the data which is going to come up? I mean, because there aren't enough doctors to deal with this.
Well, I must admit, I'm not a big government-forced type of guy. But I do think, though, that this is a supply-demand
But we
question.
can ask governments.
Right. Well, I think it's actually going to be something that doesn't necessarily have to rely on governmental pressure. This is a supply-demand issue. If we as clinicians continue to ask for better technology, and there's an example through one of our sponsors today of technology that can take the raw data from wearables and provide it to us in a more usable fashion, and we figure out a way to get financial reimbursement for that, it will absolutely happen. If we don't, maybe there needs to be governmental pressure, but I certainly would not like to see it come to that.
We're going to have one more question.
Thank you. Very good presentation. Heart rate variability. Years ago, when heart rate variability was being analyzed, you have to clean the 24-hour ECG, remove ectopics, remove the noise, to really clean the ECG before you analyze it. These devices, what's the accuracy in providing our HRV? Because, in my opinion, I get these patients that come in, they tell me about the HRV, but because I did a lot of research on HRV, I tell them just ignore it completely.
Yeah, so as most of you know who have done high-quality HRV measurements in a lab setting, it can be noisy and it takes a lot of data cleaning to get right. So how do these little things give us an HRV number? Well, the answer is they probably don't do it very accurately. And what I would say is that the absolute HRV value that gets spit out of a commercial watch is probably useless. I think there is some utility on an individual basis to tracking over time. But if that HRV number plummets suddenly, that's an arrhythmia, right? The other things on the list cause variable deviation slowly over time, but if someone's HRV drops from their personal range of 60 to 80 down to 20, that's almost certainly an arrhythmia.
All right, thank you so much.